Welcome to a brand new deep dive. We're tackling something I know many of you are thinking about. The future of real-time conversational AI.
That's right.
You know that feeling, right? When you're talking to a smart assistant and there's just that gap.
Oh, yeah. That pause.
Exactly. That slight delay that just kills the flow, makes it feel, well, kind of awkward.
Uh-huh.
So today we've got a stack of really cutting-edge research, and we're going to pull out the key insights, the nuggets of knowledge about these groundbreaking models that are really changing things.
Yeah, our mission today is really to show you how AI conversations are finally getting, well, almost indistinguishable from talking to another person.
It sounds like a huge leap.
It is. I mean, while voice assistants have definitely improved over the years, getting that truly natural, instant-spoken chat with an AI, that's still a major hurdle.
So we'll dig into that.
We will. We'll unpack the core problems, why it feels clunky now, and then really dive deep into two super innovative solutions, Moshi and VITA-Audio. And you'll see how they're not just tweaking things, they're fundamentally rethinking the whole interaction.
All right, let's unpack it then. Why do the current voice interfaces, the ones we use now, still feel so unnatural? What are the actual technical limits causing that jarring experience?
Well, it really boils down to how these traditional systems are actually built.
Okay.
Think about, say, Alexa or Siri, or even the voice interfaces for ChatGPT or Gemini. They mostly rely on this pipeline of separate parts.
Like an assembly line.
Kind of,
Yeah.
like a relay race.
Mm-hmm.
Information gets passed along. First, there's voice activity detection, figuring out if you're talking. Then automatic speech recognition, ASR, turns your voice into text.
Right.
Then that text goes through natural language understanding, NLU, and natural language generation. NLG, basically understanding and figuring out a response, but in text.
Still in text. Okay.
And then finally, text-to-speech, TTS, turns that text response back into sound. This whole chain of separate steps, well, it causes some big problems.
And I'm guessing one of those is speed. Each step adds its own delay, right? Which all adds up to that lag we hate.
Exactly. That's the first major issue. Cumulative latency. Every single component in that pipeline adds its own little delay. So you end up with a typical global latency, the total time from you speaking to getting a response of several seconds.
Several seconds, wow.
Yeah. Now, compare that to how we talk. Natural human conversation, our response times are usually just a few hundred milliseconds.
Right, almost instant.
So that massive difference, that delay, it fundamentally undermines the feeling of having a real flowing conversation. It just feels wrong.
Okay, so speed is one thing, but you mentioned it all goes through text. What gets lost when you force a spoken conversation into just words on a page?
That's the second huge hurdle, the textual information bottleneck.
Okay.
Because the understanding and the response generation mainly happen using text. All the non-linguistic information, the stuff that changes meaning but isn't words, it just gets thrown away.
Like what kind of stuff?
Crucial things. Paralinguistic cues like your emotion, the intonation in your voice, your accent. All those subtle hints that tell us how someone means something, not just what they're saying. And even non-speech sounds, background noise that might be relevant. The model basically ignores all these rich layers of communication.
That's like it's tone deaf, basically.
Pretty much, yeah. It misses so much context.
And then there's the fact that, well, real conversations are messy, aren't they? We interrupt, we talk over each other sometimes, we make those little noises.
Right.
Current AIs seem completely flummoxed by that. They just wait politely.
You've nailed the third big limitation. Rigid turn-based modeling. These systems are designed, fundamentally, to be turn-based.
One person talks, stops, the other talks, stops.
Exactly. A clean sequence of neat single-speaker segments. But real spoken conversations, they're way more dynamic, they're often messy.
Yeah.
You've got interruptions, you've got overlapping speech, which, get this, actually accounts for something like 10–20% of the time we spend talking in natural dialogues.
Wow, that much.
Yeah. And then there's back-channeling those little, okay, I see, sounds that show you're listening but don't actually interrupt the flow.
Right, the feedback cues.
Traditional systems, they just can't handle these natural dynamics well at all. It makes them feel clunky and, well, artificial.
Okay, that really paints a clear picture of why current AI chat feels so frustratingly unnatural. So given those deep problems, the latency, the text bottleneck, the rigid turns, how are researchers actually tackling this? What are the breakthroughs?
This is where it gets really interesting.
Let's start with Moshi. You mentioned it's a new speech-text foundation model. How does it aim to solve all these things at once? It sounds ambitious.
It is ambitious, but the approach is fundamentally different. Moshi basically redefines the whole idea of spoken dialogue. It treats it as direct speech-to-speech generation.
Speech to speak, so bypassing the text step entirely.
Pretty much. It leapfrogs that text barrier. It removes that textual information bottleneck because it understands and generates the output directly in the audio domain.
Okay.
But crucially, it still benefits from all the knowledge and reasoning power of a large language model operating on text internally.
Huh. So it understands sound, speaks sound, but still has that big text brain inside.
Exactly. And it's designed specifically for natural conversation flow. It's actually introduced as the first multi-stream audio language model.
Multi-stream, what does that mean?
It means it explicitly models two parallel streams of audio tokens. Think of it like two separate channels. One for its own speech and one for the user's speech happening at the same time.
So it can listen while it talks.
Precisely. This design completely removes the idea of explicit speaker turns. It lets the model handle all those messy real-world conversational dynamics, overlaps, interruptions, everything.
So it can actually interrupt me, or I can interrupt it naturally.
Yes. It's full duplex. It's constantly listening and constantly generating sound, whether that's speech or just silence, like pausing naturally. It enables that truly flowing back and forth interaction.
Wow, okay. And you mentioned it taps into a text LLM. How does it connect the audio understanding to the text reasoning? You mentioned something about an inner monologue. That sounds intriguing.
It's a really fascinating part of the architecture and key to its quality. Moshi achieves really high linguistic quality because it predicts time-aligned text tokens just before it predicts the corresponding audio tokens.
So it thinks in text first, then speaks.
Kind of like that, yeah. This inner monologue acts like a scaffold. It guides the speech generation, making it much more accurate, factually correct, and linguistically sound. The research actually points to this as having one of the biggest impacts on the quality of the speech it generates. It helps stop the AI making stuff up, those hallucinations.
That's clever. So it keeps the benefits of the LLM's knowledge, but translates it directly to speech via this inner monologue. What are the actual components making this work? What's under the hood?
So the core reasoning comes from Helium, which is a 7 billion parameter text LLM backbone. That's the brain, providing knowledge.
Okay, 7B, got it.
And for the audio side, it uses Mimi. Mimi is a neural audio codec. Think of it as a super efficient way to turn complex audio waves into digital tokens the model can understand. And back again.
A codec, right, like for MP3s, but for AI.
Sort of, yeah, but much more sophisticated.
Yeah.
Mimi is designed for really high-quality audio tokenization, even at low byte rates, meaning it captures the important details without needing massive amounts of data. It uses techniques like a split RVQ to balance semantic meaning and acoustic detail, and something called adversarial-only training, which human listeners found gave a really noticeable boost in how natural the audio sounded.
Okay, advanced audio processing linked to a powerful LLM via this inner monologue. So the big question, latency. How fast is it? Does it beat that few hundred millisecond human benchmark?
This is where the end-to-end integrated approach really pays off. Moshi achieves a theoretical latency latency of just 160 milliseconds.
Wow.
And in practice, they measure it at around 200 milliseconds.
So faster than average human response time.
Yep, faster than the 230 milliseconds typically seen in human conversation. So it's genuinely real time.
That's incredible.
And it can handle long conversations too, keeping context for up to 5 minutes.
5 minutes is pretty good context. Now, you said the inner monologue was key. Does that architecture offer flexibility beyond just conversation? Can it do other speech tasks?
That's another really neat part.
Yeah.
It turns out, yes. By simply adjusting the timing, the delay, between predicting the text tokens, the inner monologue, and the audio tokens, you can adapt the same Moshi model to become a fully streaming ASR system speech-to-text or a streaming TTS system text-to-speech.
The same model, just by changing timing.
Exactly. And it performs remarkably well. On the LibreSpeech benchmark, it got a 4.7% word error rate for TTS and 5.7% for ASR. And here's the kicker. It was never specifically trained on that LibreSpeech data.
That really shows a fundamental understanding of speech, doesn't it?
It does. It suggests the model isn't just memorizing patterns, it's learning deeper representations.
Okay, performance is impressive. But as these systems get more powerful, safety and robustness become huge concerns for everyone. How does Moshi stack up there?
They've put a lot of thought into that, which is crucial. For robustness, the training included extensive data augmentation specifically on the user's audio stream.
Like adding noise?
Yeah, adding random gain, background noise, simulated echo, reverb, basically making it resilient to messy real-world conditions and different accents.
Good. And safety, toxicity, privacy.
On safety, it scored reasonably well on the alert benchmark for toxicity, getting an overall safety score of 83.05, putting it kind of in the middle range. Very importantly, they focused on preventing regurgitation of training data.
Meaning it won't just parrot back things it heard during training.
Exactly. Through careful data deduplication and fine-tuning techniques, they found it exhibits zero regurgitation, even when you try to prompt it with bits of audio that were very common in its training set.
That's reassuring. What about the voice itself? Does it start sounding like the user?
No. And that's another key safety consistency point. It demonstrates strong system voice consistency. It sticks to its intended voice and doesn't mimic the user's voice. They measured this at 98.7% consistency, and it stays stable over time.
Okay.
The research also mentions the challenge of watermarking AI-generated audio, noting that current signal-based methods aren't very robust if the audio gets compressed, like in streaming. So that's still an open research area.
Right, and practicality. Can you actually run this thing efficiently?
Yes, it can be compressed using quantization. Interestingly, its linguistic performance is more sensitive. It drops off significantly below 6-bit quantization. But the audio quality holds up well down to 4 bits.
And a 4-bit model is much smaller.
Oh yeah, it's 3.43 times smaller than the original, with only a small drop in its language understanding scores. So definitely practical for deployment.
Okay, so Moshi is a massive step forward, integrated, multi-stream, fast, robust, safer. But you mentioned another model, VITA-Audio. What if you wanted to push latency even further, like right down to practically zero? Is that even possible?
Well, that's exactly what VITA-Audio aims for. It tackles a very specific but critical bottleneck that even some end-to-end models still have.
Which is?
It's called the first audio token delay. Even if a model can stream output, there's often still this tiny but noticeable pause after it figures out the first word of its response, but before it actually starts generating the sound for that word.
Ah, the time between thought and speech, almost.
Exactly. VITA-Audio's big goal, and its achievement, is zero audio token delay and zero audio generation delay. It aims to start speaking the instant the first part of the response is ready.
How on earth does it manage that? That sounds incredibly difficult.
The magic is in its core component.
Yeah.
A lightweight module called the Multiple Cross-Modal Token Prediction Module, or MCTP.
MCTP, okay.
Now, instead of generating one audio token at a time based on one text token, this MCTP module is designed to efficiently generate multiple audio tokens specifically, 10 of them within a single forward pass of the main large language model.
10 audio tokens at once, per step.
Per LLM step, yeah. This direct multi-token generation is the key. It gives VITA-Audio a remarkable 3 to 5 times inference speedup compared to other models of the same size, like 7 billion parameters.
So it's predicting sound much faster by doing it in bigger chunks, essentially. How does it know which sounds to predict from the LLM's internal state?
That's based on a clever insight. The designers realized that the hidden states, the internal representations, from the LLM's final decoder layer already contain enough contextual information to figure out the corresponding audio tokens.
So the LLM does the heavy lifting of understanding, and the MCTP just needs to translate that final thought into sound chunks.
Exactly. That simplifies the job for the MCTP modules. They don't need to do complex semantic modeling themselves. They just map the LLM's output to audio, making it super fast.
But does that speed compromise the quality? Usually there's a trade-off, isn't there?
They address that with their modeling approach. VITA-Audio uses an interleaved modeling paradigm.
Interleaved.
Yeah, instead of having separate streams for text and audio like Moshi, it combines the text tokens and audio tokens into a single sequence that the model processes. Research found this approach actually better preserves the language capabilities of the base LLM compared to parallel modeling, so it helps maintain high quality alongside the speed.
Interesting. And is VITA-Audio accessible? Is it based on proprietary data?
No, and this is a big plus. It's trained exclusively on open source data sets. We're talking massive amounts, hundreds of thousands of hours of publicly available ASR, TTS, and spoken question answering data.
So the research community can build on it.
Exactly. And despite using only open data, it achieves state-of-the-art performance. It significantly outperforms other open source models of a similar size on standard benchmarks for speech recognition, text-to-speech, and spoken question answering.
That's impressive for an open model. How did they train it to predict multiple tokens reliably? That sounds tricky to get right.
They used a specific four-stage progressive training strategy. It's designed to gradually teach the MCTP modules how to do that mapping from text context to multiple audio tokens efficiently and accurately, ensuring stability.
Okay, a careful training process. And does it offer flexibility? Can you tune the speed versus, say, how quickly it generates text?
Absolutely. It offers different interleaved inference modes. There's Turbo, which
Mm.
is the fastest. It generates one text token, and those 10 audio tokens per LLM step,
Max speed.
right? But there are also modes like Boost, Balance, and Vanilla, which adjust that ratio so users can choose the best trade-off between raw speed and maybe letting the text generation get slightly ahead, depending on their specific application.
Very cool. Okay, so we've gone deep on two really different but incredibly innovative approaches here. We have Moshi with its deep speech-to-speech integration, the multi-stream architecture handling interruptions, the inner monologue,
A real-time flowing conversation.
and then VITA-Audio, laser-focused on crushing that first token latency, getting down to zero delay with its clever MCTP module and interleaved modeling.
Yeah, pushing the boundaries of instantaneous response.
So, stepping back, what does all this mean for you, the listener, for the future of how we interact with computers, with AI?
I think these models represent a truly significant leap. We're moving towards conversational AI that feels, well, completely natural.
Like talking to a person.
Pretty much. Imagine having an AI assistant where there's no noticeable lag. It responds instantly, it can pick up on your emotional nuances, understand your accent, and crucially, it can handle interruptions and overlaps seamlessly, just like a real conversation partner.
That would be game-changing.
And because these models, especially Moshi, can process and generate that non-linguistic information, our interactions can become so much richer, more expressive. We move beyond just asking for facts to having genuinely engaging dialogues.
Yeah, conversations with personality, perhaps?
Potentially, yes. And this breakthrough in real time, natural speech opens up so many possibilities for new applications. Think more responsive virtual assistants, truly immersive interactive games or entertainment, dynamic educational tools that feel like a real tutor.
The possibilities seem endless once the interface feels natural.
They really do. And importantly, the focus in the research on things like safety, voice consistency, preventing data regurgitation that builds a vital foundation of trust, which we absolutely need as these systems become more integrated into our lives.
It definitely feels like we're moving fast towards a future where our digital interactions aren't just about understanding words, but about understanding us, with all the subtleties of how we actually speak.
It's like AI is finally learning to speak human, not just process language.
Yeah, exactly.
And maybe that leaves us with a final thought for you, the listener, to consider. As these AI conversations become potentially indistinguishable from human ones, how might that change our own communication, our expectations for interaction, both when we talk to AI and maybe even when we talk to each other?
That's a deep question. How will we adapt when AI becomes just another conversational partner in the room? Definitely something to mull over.